Hey everybody, and welcome to Passive House Accelerator Live, where we explore how to create healthy buildings that both slash greenhouse gas emissions and make us more resilient to the impacts of climate change. We'll dive into how passive house design principles are applied in the real world and how these buildings improve the lives of the people who live, work, and play in them. On the first and third Wednesday of the month, we'll feature the Project Showcase edition of Passive House Accelerator Live. And on the second and fourth Wednesdays, we'll feature the Construction Tech edition. Every Wednesday is for the Passive House newbie and the Passive House expert alike. If you are new to Passive House, check out the 101 section of our website for a primer. With that, please enjoy this Construction Tech edition of Passive House Accelerator Live, co-hosted by Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey. And as questions occur to you during the show, please type them into chat and we'll get to them during the discussion session. Thanks.
This month on Passive House Live, we are talking about airtightness. Last week, we had Ed May on. He described 10 ways to ace your blow a door test. I'm going to try and dive down into a little bit of technical technology and the technique of air barrier systems, but airtightness is quintessential to Passive House. Airtightness has driven my career. Early on, if you watched the Dense Pack episode, I went through the career path, which I've had. I started in weatherization. And early on, I was able to learn how to use a blow-a-door. And using the blow-a-door, I was able to solve so many problems because you make the invisible visible or you make the invisible tangible. Very early on, I was taught that anything that can't be measured can't be saved, and you can't hold people accountable. So airtightness has become almost like a level of pride in my world of energy efficiency. So I would always ask at conferences before I discovered Passive House, like, hey, what's the best blow a door number you ever got? Like, how low have you been able to go? You know, airtightness is a good thing, but how low could we be able to go? So that's kind of like where my drive has driven me. So we'll take you on this little journey here through my slides. So my name is Kevin Brennan. This is Smart Airtightness Strategies. That is my former lighter self, working on the Cornell Tech project, doing blow-a-door testing on a 27-story building, checking room by room, apartment by apartment, little leaks by little leaks to make sure that that project hit its airtightness goals. I was brought in by the GC team to be their kind of like their airtightness supervisor. And please excuse me. And we did a decent job. We hit our goals on that project that nobody thought was achievable. So when we say smart, the word smart, in my opinion, means specific, measurable, achievable, realistic, and I can't see the T because of the chat here, and timely, all right? So when we say timely, meaning it has to happen on a budget, at the right time. So I've been teaching the Passive House Tradesperson course for about 8 years now, and it's been a great experience to get like-minded people in a room and to talk about energy efficiency in Passive House. It's very exciting to see the change process that happens when teaching somebody about the best of building science or building better, or as I would like to say it, putting your boots on, going to work and doing the best you can to make the best building for not today, but tomorrow. It's something I take pride in, and it's something the people on my team take pride in. So by teaching the tradesperson course, I've shared that experience with other people, and I was like, I want to do this work because I'm a doer. I want to actually put my hands on the work, get it done, and prove that my knowledge, skills, and ability give me the option of doing that. So I started Brennan Insulation and Airtightness, and that's what we focus on: dense packed cellulose, installing air barriers and insulation systems. And the only kind of trick that's in our thing is that we use all the tools and the technology in our arsenals. We do our own testing up until the end, and then we have a third party commit if we need. Why is air tightness so scary, right? So I have a conversation with the builder. You can do Passive House, and they are terrified, absolutely terrified of air tightness. Because why? Because it's the fear of the unknown. They've never done it before. So everyone's a little scary to walk in the dark at night and not know how to get there. And that's the theory. That's the problem with airtightness, is that you can't touch it. You can't feel it. It's something that's very unknown. General contractors, kind of like project managers, are afraid of it because they haven't done it before and they don't know the process. It's not a common practice to shoot for super airtightness and to put your money where your mouth is on a project, to say that I'm guaranteeing this airtight project. The other reason why it's very scary for people is the details are hidden inside the wall or under the cladding. So if you keep your schedule going for the project, whatever you're working on, you only get one chance to kind of fix and see them. So it is, we acknowledge that it is a scary process, but like everything in life, it takes technique. And the technique is, I'll go through it, as being smart. And the way it's being smart is using the systems, is what I say, and using a model. So over 25 years ago, PHI started Passive House with Dr. Feist's project, and they hit airtightness. They hit super airtightness. They hit I want to say 0.25, 0.3 air changes per hour on that first project. And they set the standard slightly leakier at 0.6 air changes per hour. So PHI's new construction airtightness standard is 0.6 air changes per hour. The retrofit, the common buildings I work on at brownstones, is 1 air change per hour. And I didn't put it in the slide because it's really not relevant, but the New York State code minimum requirement right now is 3 air changes per hour, okay? And when you read the code and you read the documentation, all it says is continuous air barriers from top of wall, all the connection details, no voids, it's penetrations filled. So if you looked at the wording of the code, it says you need a continuous air barrier. The difference between a continuous air barrier at 0.6 air changes per hour and 0.3 is the level of, it's the tolerance. It's the, how many mistakes are you going to allow? How many penetrations are you going to allow to go unsealed? On the other side of the coin, we have the FIAS projects. And FIAS has taken a different approach towards airtightness, in that instead of measuring the volume of air inside the building, they're going for the Q50 number, which is the permeance of the surface area of the building. So a bigger building, same number. Whereas if you have a larger building with a high surface area to volume ratio, it's going to be easier to hit 0.6 than it would be with the Q50 number, which is for non-combustible, it's 0.08. And for all the buildings, it's 0.06 at 50 Pascal. Then there's the prescriptive path as well through FIAS, which I'm not as familiar with, and that is 0.04. So if you can hit 0.04, that's the prescripted single-family detached townhouses. They also have a slightly different method of measuring the airtightness. They do an air barrier integrity test where they mask up all the intentional openings and measure only the airtightness of the air barrier, and then they do one with the masking removed. So there's just slight nuance difference between the two testing standards. The FIAS one takes on ASTM 779, which is an American standard, and PHI takes on the EN 13829, which is a European norm standard. Both are the very similar processes. So I'm done with the nerd numbers. You guys can all wake up now, and now we're going to move on. All right. So when we talk about air barriers, we have types of air barriers. We have rolls. All right. So the rolls, self-adhered membranes, which are Peel and Stick, Henry, Suprema, Grace. We have mechanically fastened membranes, which are your Tyvek, your Typars, Proclima, Intello, the Sega membranes, internal, external, Partel, all different mechanically fastened membranes that go on the wall. They're able to be an air barrier, and they're either stapled or glued, or they're cap screwed onto the wall, either inside or outside. And then the next types of products we have buckets or fluids, and those fluid applied membranes could be Stowe, Carlisle, Partel's fluid applied membrane, the Viscon, which we've had a few videos on and going across. And then we have sheets, so sheet goods. We have the zip system, which is very popular in the U.S. market here, of installing your sheathing with an air barrier on it and treating the seams, treating the seams, not the sheams, the seams. We also have the AC grade plywood, which is common that we use on the brownstone projects, because a lot of the GCs that we work with, their background in history is carpenters. They like installing heavy, robust walls. But the AC grade plywood, as we know, the price has gone through the roof with the pandemic. So when we say AC grade plywood, it's A face, which is no knots, no defects, 3/4 inch thick. The C grade is on the other side, maybe some knots. It's just a level of quality that is required. You could take the chance of using OSB, but there has been chances of it being not airtight over time. Chris Corson has a great story about how he knows Zender's ERVs float, and it's a great story. We'll get him on to tell it one day. So the strategies of hitting airtightness, all right? My number one strategy is choose an air barrier system and stick with it, right? So if you choose Proclima and you use an Intello or Viscon, stick with the family of products, the Vanas, the Profil tapes, the Solitos, all within their range from inside to outside to the window, all the way around with one system, so that you can go from subgrade, connecting to the vapor barrier, subgrade, up the wall with the membrane, and then all the seams are taped with the common tape with the pressurized acrylic adhesives, and then marrying it up to the roof and the ceiling with the Intello on the inside. So you have one air barrier system that connects all the way around. And then one of the things that Ed mentioned last week was that red line test. That red line test is a great check two-dimensionally of your air barrier system. I live in a three-dimensional world, and my three-dimensional world, I need to make mock-ups and I need to check those details. So every time Ed said you make that circle and you check a detail, I'm going to go in with my team, the GC, and we're going to do like a mini mock-up. We're going to rough that out. We're going to see, I'm going to push that system to the edge of when it's going to fail. Because 90% of the time when those systems fail, it's because we didn't read the instructions, and all the systems need to be clean and dry to stick. I could show you some horror show pictures of the first project we worked on, but let's stay positive here. So the other strategy towards airtightness is test early and test often. All right. So this picture on the far left is a picture of a Minneapolis duct tester in the Rochester Passive House, done by my friend Matt Bowers up in Rochester, and his team that did that project. And I was very lucky to meet Matt at the tradesperson course. They came down from Rochester to take the tradesperson course, and I followed this project along on his blog. And they were able to take a blow-a-door and put it in the window and test as they went along. So as soon as their windows were in, their air barrier was complete, they kept testing early and often. The picture on the right is of an apartment that's semi-finished, that the air barrier is up on the wall. And we're testing and trying to find the little mistakes before they get hidden. The general rule of thumb is, before you put up the finish in the sheetrock, that you've gone through and checked or have confidence that those systems that you've put in place are as airtight as you potentially could make them. Either they've been checked with visual inspection or they've been checked with pressure and smoke. Visual inspection goes a long way, but when you have a new team and a new system that doesn't know what mistakes look like, I'll show you some instance of it. You have to kind of like train their eyes how to see the invisible. One of the goals of my projects that I work on is to get the air barrier on the wall, cover the windows, cover everything with the membrane, and then run my blow-a-door. And I have one solid air barrier all the way around all 6 sides of the project. And then I know my air barrier system is at 0.3 air changes per hour. And then my next blow-a-door will happen when the windows go in. So now the windows went in, and now we're at 0.4. which got slightly leakier. And then all my penetrations happen, HVAC, electrical, everything's happening there. They've been all detailed. The front doors go in, the complex systems happen, and we're at 0.6, and our goal is 1 air change per hour. That is a testing plan, and that's something that needs to be coordinated. One of the goals of my career that I hope to see is that on a set of plans, everyone has a detail of the Passive House plaque that goes on the wall, that it's detailed there because you have confidence that you're going to achieve it. And the other thing that I would love to see on every project is scheduled blow-a-door tests on the Gantt chart of the schedule. That is, that blow-a-door test is drywall can't happen until we pass our initial blow-a-door test. All right. Windows can't be trimmed out and finished until we pass our blow-a-door test. Final handoff, the ERV commissioning can't happen until our final blow-a-door test is in place. Kind of, that's your testing plan, is what I hope. So here is I'll play this a few times, but you're going to use the blow-a-door as a tool. And the tool to find the leaks and check the work using pressure, my trick of my trade is to take a fan somehow, put it in the building, either in a window, a back door, through a skylight, a negative air machine, a fan in a can, doesn't matter what it is, but somehow I'm building pressure on the building, either at 50 Pascal or 25 Pascal, and I use that smoke stick with pressure to find every one of those leaks. This was not one of my projects. This is a project I was hired to do a blow a door on, and the air barrier was, not really, it wasn't executed that well because the team wasn't trained on that. Every one of those joists need to be cleaned. They need to be sanded down. That 100-year mummy dust that's on that joist needs to be broken down to its original fibers, and all those gaps and cracks need to be filled with either a sealant, a foam, or mortar, and then coated with the air barrier on there. It also needs to be clean and dry. That pile of dirt and dust and debris down at the bottom there does not let those air barriers stick. Plus, this is a very difficult spot to work on. This is the front of the building. Your head's up in a joist. Not easy to do. All right. How are we on time? We're running pretty good. 7:20, not too bad. Air barrier, installing air barriers is an art and a science. I never considered myself an artist, more of a fartist than anything else, but it's a science. So you balance the art of your craft and the perfection of installing something. The first time you do it, it's a mess. It looks like a Picasso painting, and then you get a little better, and it starts to look cleaner and better, and more. The lines are starting to come together, and then at the end, it's like, oh wow, I'm getting really good at this. Everything looks perfect. It is perfect. And the science of airtightness is knowing the technical capacities of your materials, and those technical capacities of your materials is it going to stick? Is it going to be long-term and durable? Did I read the instructions? Are they clean and dry? If I'm using fluids, the fluid applied air barriers, what thickness do they need to go on? How do I check that they're on at the right thickness? And is it fully adhered or semi-adhered? So, it's the craft of airtightness is and the skill and the goal of me sharing and being a part of Tech Tuesdays is to create air barrier installers of tomorrow that go to work and get paid really well and take pride in their work throughout the world. I'm an air barrier installer, and that's a job title as if it was just as if you were a carpenter or a plumber, but you're taking great pride in it. Just like the pride craftsmanship of a Finnish carpenter. You can't tell a Finnish carpenter to hurry up, just get it done. They'll walk off the job and they'll say it's either done perfect or it's not done at all. And that's the same integrity that you need as the air barrier installer, because perfection takes time. It takes the ability to work clean. It takes time to check it. So you're shooting for perfection. One of the on my prep for this session, I listened to one of the podcasts by PHI Georgia, what's her name, and they said there was a German phrase in Germany that you pay to do it right once or you pay to do it twice. And I think that's what we really need to develop in all culture as well, because do it right once or do it twice. It's that same way, because installing an air barrier comes through. The next strategy or process that I like to do is mock-ups create teamwork. All right. It's a complex detail like a window and a wall needs to be coordinated by the team. So that is the architect of the project from Mike's team. That's Frankie. That's a back Stingway project. And the GC needed a corner sample of the window. So with the technical details, the Finnish carpenter made a mock-up out of plexiglass and wood to scale that was spot on and perfect. And we talked in that rough opening of like, what were the critical details of that? It needed to be drained to the outside. There needed to be a backstop. It needed to be flashed at the bottom. How are we going to make it airtight? We're going to use fluids going to the inside, to the rough opening. We're going to tape it on the outside. We're going to tape it on the inside. What were all the details that were going to need to get done? The gentleman on the left is the window installer, and then we were responsible to make it airtight from the inside. He was responsible from the outside, and it's that coordinated teamwork that needed to happen. But a mock-up breaks down barriers, brings people to the place where the work is happening, and you're able to cognitively talk about how you're going to install that window. If you could do that at every one of the round circles on Ed's red pen tests, you have great teamwork, and you've got a process of trying to almost like find where your failures are going to be before they actually become failures. So, all right. So here we're going to talk about technology. So part of Tech Tuesday, or former Tech Tuesday, I'm sorry, Wednesdays here, was technique, technology, Tuesdays, and I'm screwing this up already. It's been a long day. So the technology that I'm going to bring is infrared cameras. All right. So infrared cameras do help me see the invisible, but I can't see anything with air tightness unless I'm running a fan at some pressure. So what this image shows is that by running a fan at 5 Pascal, I see a little bit of leak. 10 Pascal, I see a little bigger. 25, I see a real big leak. And then 50 Pascal, I see a very large leak. And I can start to see that streaking that's happening, bringing the cold air from outside to inside. And I can see those defects. Otherwise, they are completely invisible to the naked eye. The sad part of this reality is that the infrared cameras and the leaks really don't work that well on thin membranes. So it has to go over a hard surface to really develop that streaking that we see in this picture. So it would be more of a finished blow-a-door test. But I have used the infrared camera to find leaks, like water leaks in the membranes and things. But it is a tool to use so that you're scanning the building smart and being smart about it. The next tool here is called a hot wire anemometer. It's just an electrical device that measures the quantity of air going past. It's a wand that can telescope, and there's an air barrier on the wall there. And that's measuring that there is a very large leak there at 14 to 1500 feet per minute. So we're actually measuring the amount of air going past that device there. It's a very sensitive device. So with the fan running either negative or positive pressure, I can read the numbers that it's happening. And I can quantitate how much leakage, what a big leak is and a small leak is. Whereas with the smoke stick, I can only say that's where the leak is. I prefer the smoke stick because it tells me exactly where to seal, and I have to figure out how do I solve and plug that hole. This is the next reason why you would use a smoke stick, is because it helps you find mistakes like this. This poor innocent, very innocent, prideful HVAC installer just didn't know that membranes melt. He just didn't know that taking a torch and brazing the HVAC pipes would melt the plastic and potentially burn the project down and ruin my air barrier. But we're able to find it, solve it, and fix it by doing a blow-a-door test and showing him and bringing him by the hand and be like, bro, this is what happened. You can't do this. And the GC has to help the teamwork there. This is the sheets, installing the sheets in that roof using a little bit of technology of the pneumatic stapler going across there, and good teamwork and training the people installing the membrane, how you do it, why you do it, and what airtight is. So the technology of air barrier systems is using smart grommets that reduce labor but make the job easy. I give that grommet to a plumber or an HVAC guy. They install it on the pipe, and then I come back and I put 3-4 strips of tape on it. I press it, it's clean, it's dry, and it's 100% sealed. Otherwise, it would take me manually, 10, 15 minutes to clean it, to prep it, to put it across. Technology of installing self-adhered membranes with an innovative process. This is the 3M product at an air barrier training. They're rolling the membrane up and then pulling the release paper off and down. A very nice technique. They also have a vapor open product as well, which is kind of cool. So air barrier systems going in. I like the 3M membrane on certain wall types because it's opaque. You can see through it. And translucent is what I should say. And you can see where the screw heads are, defects might happen. But I haven't had the ability to work with the product yet on a commercial building. Next one is a pull test. So if your job recommended a self-adhered membrane that should be fully adhered to the outside of the building, and you want to check the adhesion, you check the adhesion by gluing a disc on the outside and then doing a pull test. And the pull test should be fully adhered. And there are certain numbers that go along with it. This is a part of the ABAA process. The ABAA process, and it's 3 discs equal 3 tests. Next one is the fluid applied air barriers, which is one of my favorite parts of the latest process of installing these flashings, is that it makes 3-dimensional inside corners, outside corners kind of easier. And that gun you see there is a 12-volt sausage gun that installs, instead of breaking your hand the next day, especially in the cold, it's installing that membrane nice and easy. This is a This is the product from, this is Prosoco. This is Prosoco's product, and you'll see some of this on the showcase next week. But you can see that the gentleman there using a hand sausage gun and then smoothing it out. The real trick to this is just making sure it's on at the right thickness. Each manufacturer has a different thickness. And where would you find such details? You would find it in the technical data sheets. So one of the parts of the training is to get people to read the technical data sheets, read the instructions, know the limitations of the products. And sometimes that happens in a mock-up, sometimes that happens in a training, sometimes it happens by a good team and a bunch of nerds going through it. This is a blow-a-door test on a 4-unit building for code compliance. It's a little shocking there, but I have 4 blow-a-doors going at once to test a 4-unit building for code compliance. It's a small fan and a big fan. Go up the stairs, all to the other, and I've got 2 more fans running. So the point here is that any building can really be tested, large or small, by coordinating the fans and putting them together. By getting equal pressure on all 6 sides of the building, you're getting a very good testing process. And this is, I don't know if you guys have sound or can hear sound. I doubt it. But this is my good friend, Jason Andres, another Passive House tradesperson, that I asked him, what would you think if I told you the blow-a-door test results were 0.32 on your test at rough-in? And he was like, oh yeah, that's awesome. 0.28, 0.29. It's one of the tightest projects I've ever tested. And that is a self-adhered membrane on the outside. And that's a perfect time to do your test, is when it's rough-inned and everything's done. And him and the guys that work on his team are very proud of that. But you can see my cachet of tools there, the hot wire anemometer and the smoke stick, ready to check and find leaks. But I was a happy guy that day because there were no leaks to check and find. It was a very good system done, and proud team. This is a troubleshooting a window of doing a ASTM 783 test, building a chamber on the inside, testing one of the windows, blowing smoke on the outside and pulling air in the chamber built on the inside, and trying to video if there were any defects within that chamber. So that's a large amount of smoke, and it's not easy to see where it's coming in. I like the small smoke stick pointing me right to where the mistake is. This is probably a Blair Witch sweaty project of a chamber that we build on multifamily projects. And it's a chamber big enough to where somebody can go inside, depressurize it, and check all the details with a small smoke stick. And that's called what we call the dirty Passive House 783 test, is that we boost it to 50 Pascal, like the final test pressure, and we troubleshoot and find all the leaks from the inside with the smoke stick or even the hot wire anemometer. This is us inside the box here with the smoke stick, trying to find where the leaks are.